In this video, I will walk you through the derivation for spectral modularity maximization. This is a nice analytic way of doing community detection using modularity. There's a number of other methods that use modularity for community detection, and then there are also methods that don't use modularity in order to find communities. So when we first looked at modularity, modularity was a way of quantifying, given a set of classes, how much the network, essentially the edges, represented connections between nodes of the same type. When we do community detection, we don't actually know the node classes, so the CI, CJ labels are unknown, and that's actually what we're trying to find. So we're going to assume that nodes of the same type will be connected, and so we're going to assign labels that actually make that true. So essentially, we're going to, instead of computing what Q is, we're actually going to try to maximize that. And so keep in mind that maximizing modularity is a proxy for finding communities. It's not the only way to define that. But in this case, it's a nice analytic tool, and I thought that this video would be helpful because this derivation uses a number of tools that you may or may not have seen before. So remember, this is our definition of modularity, where this term comes from the number of edges, the fraction of edges that connect nodes of the same type, and this is the random baseline that we're comparing to, essentially at random, while we preserve the degree, what is the expected fraction of edges that connect nodes of the same type. If we define this matrix as B, then the B modularity matrix, then we can rewrite it like this. And so obviously once you have the adjacency matrix, you can also compute Ki and Kj, and so you can compute Bij as soon as you have the adjacency matrix. So we're going to use several tools here. The first one is that we're going to rewrite this Kronecker delta in a little bit more of an analytic framework, and we're going to be aided in this to this end because we're only going to include the possibility of having two different types or two different groups. So oftentimes, you can read about this in the textbook, that if we have multiple types, or we expect that we have multiple types, then typically most methods are binary methods. So they essentially find two groups, and then you can run that again on you can run the same method again on one of the groups to bisect that in half. So we're going to consider just two types. So we're going to not use CI and CJ, but now we're going to label this SI, essentially the class of node I, being plus or minus 1, and that's going to denote the two different groups or classes. And so then if that's the case, then what we can do is we can rewrite this delta function, being a little tricky, like this. And so if CI and CJ are both minus 1, then this term is 1, and then we add 1, we get 2, and divide by 2, we get 1. If they're both positive 1, then the same thing happens. But if they're opposite, 1 is plus and 1 is minus, then this ends up being minus 1, adding with this plus 1 gives you 0. So that means that essentially the Kronecker delta for two classes can be quantified using this trick. So if we substitute that in for delta, then the equation for modularity becomes this. And so in the lab, you're going to go through the process of showing that essentially this plus 1 term, when it gets multiplied by this Bij, ends up going away. And so that leaves us with just this term, which if you rearrange this using the index notation, you'll realize that this is actually two matrix multiplications. In particular, if you factor out this SI outside of the J sum, because it's not dependent at all on J, then what you're left here is essentially a matrix multiplication between the matrix B and the vector S. And so you're summing up over J, so this represents the product of B times S, and you're going to be getting the ith element from that. And so then multiplying si with this term sub I, that is another vector-vector multiplication, and so this boils down to this quadratic form, S transpose BS. Quadratic forms have nice properties, and so what we're going to do is we're going to want to maximize Q, and this is our definition of Q, when Si is either -1 or +1. So this turns out to be a pretty tricky problem. This is actually what's called an integer problem, integer optimization problem, and so those are challenging. And so what we're going to do is we're going to use what's called a relaxation of the optimization, and that means that we're not going to think of S now as plus and minus 1. We're going to now think of it as a real number that lives between, well, probably between -1 and 1, but it's really just a real number. And then to make sure that these don't just do anything that they want to do when we plug this into the optimization, we're going to add a constraint that essentially tells us that if we square all the terms of this S vector, that they should add up to be n. And so this comes from essentially the fact that that S transpose S just does exactly this constraint. And so if S1, S2, and so on are either plus or -1, then this would indeed add up to be n anyway. And so this is a term that helps to constrain the elements of S so that they're somewhat close to plus or -1 on average. And so they're not just any value. And so now this is a much more tractable problem that we can solve using some tools that you may be more familiar with. For example, essentially just finding where the derivative is equal to 0. And so we're really using the fact that this quadratic form is this generalized notion of a parabola, and so it has a definitive minimum or maximum. So if we find where that term is equal to 0, that gives us essentially the minima or maxima. So if we took derivative of just this term, S transpose BS, that would be this term, but now we have this term that is a constraint, and so this is something that you may or may not have seen before, but one of the techniques to imposing a constraint on an optimization problem is to add it as part of the cost with what's called a Lagrange multiplier. So this is some parameter, and it gets multiplied by essentially the value of the constraint. So in this case, we're taking this constraint, n is equal to S transpose S, and just solving for one side. So we just have n minus S transpose S is equal to 0. And so ideally, if the constraint is satisfied, then this enters nothing into the cost of the optimization. So it doesn't subtract or add from the cost that would represent the modularity Q. And so if we take this derivative, so this is a derivative with respect to the decision variable, S, all the S's. And so this is actually, this S is a vector. And so now we're taking the derivative where this is a vector. And so this is also something that you may not have seen before. And so if you go through the derivation on the next slide, you'll see what a quadratic derivative looks like when it's in vector form. It's nice. It actually works out very similar to what you would do in scalar form, but it's worth looking at that derivation to make sure you understand why. What ends up happening is that this ends up becoming 2 times b times s, and then this term here, beta times n, doesn't depend on s at all, so it goes to 0, and you're left with another quadratic term, S transpose S, that we take the derivative of, and that gives us 2S. And then we keep this beta term that's multiplying it. So that's equal to 0. We're finding when, for what values of S, this is actually equal to 0. The 2's cancel, and we can move the beta S to one side, and we get this equation, which maybe doesn't immediately look like it, but you can see that this is a matrix, this is a scalar, this is a vector, and this is a vector. And so this is actually an eigenvalue eigenvector equation. So S is an eigenvector, and beta is the corresponding eigenvalue. So this is already kind of interesting. And so now what we do is we try to understand which choice of eigenvector gives us the maximal value. And so if we want to maximize this quantity, 1 over 4m times S transpose BS, we can plug in the fact that we know that S is an eigenvector of B. And if we do that, then this quantity B times S, because of this exact relation, we can replace that with beta times S. And so that gives us the expression, this beta comes out, this 4m is a constant, and then we have S transpose S, which by virtue of this constraint is essentially going to be n. And so that's also a known value. And so the only thing that changes with our choice of S is going to be this beta value. And so since we want to maximize Q, we want to maximize this whole quadratic term, then we're going to try to maximize beta. And so that for that reason, we picked the largest beta. And that means that then the eigenvector, the solution S that corresponds to the maxima, is then when this S is the eigenvector that corresponds to the largest eigenvalue. And so this is the eigenvector, this largest eigenvector that corresponds to the largest eigenvalue comes back to haunt us again. The one caveat is, of course, that this eigenvector is not guaranteed to be plus or minus 1. In fact, it's almost going to be guaranteed that it's not going to be plus and minus 1. It's going to be some real values. And so what we do is we essentially now have to project that back onto what we actually want, either class 1 or class 2. And so what we do is we say that if the element is greater than 0, then we give it the plus 1, we bump it up to plus 1. And if that element is less than 0, then we give it the label minus 1. So effectively we're taking the sign, where that either takes plus or minus 1 of the vector 1, which acts element-wise on that vector. So this is compelling because it gives us an analytic solution for finding communities in a graph to maximize the modularity. And so this is one way of identifying which communities, essentially group 1 or group 2, the assignment of nodes would be in order to maximize modularity.